Okay, let's start with another example. Suppose you have x squared plus 3 y double prime plus 4xy prime plus y equals to 0. Let's try to solve this in general. So this time I'm not going to give you the initial conditions. We're trying to solve this. Okay, first of all, just plug those y double prime, just plug easy. Okay? So you do sigma n from 2 to infinity n minus 1 a n x to the n minus 2 plus 4x times sigma n from 1 through infinity n times a n x to the n minus 1 plus sigma a n x to the n from 0 to infinity. Okay, so this is what you get if you plugged in these basic formulas into the left side. Okay. Now the next thing you want to do is to multiply this to inside, right? However, our method of solving requires organizing everything in terms of like terms. So you need the same exponents of x. And this does cause a problem because if you have x squared plus 3 multiplied inside, one term will be x to the n, whereas the another term will be just x to the n minus 2, right? So there will be two terms. If I multiply this to inside, there will be two terms with different exponents of x. And that's not good. So what we are going to do is we're going to split this into two. So we will have we'll basically do this. This times this, and this times this. So we're going to distribute like that. Okay, so this times this one. What happens? That's sigma. When x squared is multiplied to this, you get n minus 1 a n x to the n. Right? And then when this is multiplied to this, 3 gets multiplied to here, so you get sigma n equals to 2 to infinity n times n minus 1 a n, oh, there should be a 3 here, x to the n minus 2. And then this one, 4x goes inside, and you get plus sigma n equals to 1 through infinity 4n a n x to the n. X to the n is created by multiplying x to the n minus 1. 1 plus n minus 1 gives you n. Plus sigma n from 0 to infinity of a n x to the n. So that's what you get if you split this. I mean, sometimes people just say, before you plug this in, just replace this x squared plus 3y double prime. Just replace this one as x squared y double prime plus 3 times y double prime. Yeah. If you multiply y double prime like that and then plug in, you get this same thing. Yes.
But you do the shifting first and then.
No. That's what I'm trying to say. You don't want to do the shifting first and do this, because if you just multiply them inside, you will get x to the n and x to the n minus 2, which requires, this one requires shifting, whereas this one doesn't. So that's, you really want to have two different summations. Okay. So now we have 3 factories. No, actually 4 factories. 1, 2, 3, 4 factories, and one of the factories needs shifting. Which one?
And my fill.
Yeah, this one, right? And n has to become what? N
Plus.
You have to replace n by n plus
N plus 2.
2. N plus 2. So let's do that. And so if I have n plus 2 equals to 2 and solve for n, what do you get? N plus 2 equals to 2. This thing becomes that. If you solve for n, you get
0.
N equals to 0. And if I replace this n by n plus 2, n plus 2, n plus 2, and everything, just think about what it's going to produce. So let's just, I'm becoming lazy. I don't want to write everything again, so I'll just replace it. So it should be n plus 2. n plus 2 minus 1 is n plus 1. an plus 2, x to the n. That's what you're going to get, okay, after shifting. Okay, we've shifted, and now everything is in terms of x to the n, so we're happy. Now we can just keep track of what the factories produce, and once all the factories start producing things, then we can write them as a single sigma, which will yield a recurrence relation. Okay? So let's try that. Okay, so the morning began. It's the 0th hour. Which factories start producing items?
The last one.
The last one and the second one, right? Yeah. So those two produce, but the first and the third does not produce anything. Therefore, we have to do this separately. If I plug in 0, this gives you 3 times 2 times 1, a of 2, x to the 0th is 1. This doesn't produce anything. This produces plus a0. That's what corresponds to the 0th hour, right? Okay, plus. Now what happens in the first hour? Do they all produce something? No, the first factory is still not working. Okay, they're really lazy. They only began making stuff at n equals to 2. Okay, so it's these three. Okay? And because it's the first hour, everyone has x to the first power. So it's something times x to the first power. So let's try to fill in what they have. This one is 3 times 2, a3. And this one is plus 4 times 1 times a1. Let's just put 4a1. And then this one, when you have n equals to 1, you get a1.
This is for n equals 0?
No, this is n equals to 0, this is n equals to 1. Yeah. So sometimes it's helpful to annotate where they came from. This is the case when n is 0. This is the case when n is 1. And then starting from 2 or above, what happens? Everything produces, right? So we can say sigma of n 2 or greater after 2. All of them produce something, so we can put this gigantic summation of n times n minus 1 an plus 3 times n plus 2 n plus 1 an plus 2 plus 4n an plus an x to the n. And the first two, if you solve it, will give you a2 and a3 in terms of a0 and a1, whereas the last one will give you the recurrence relation. Okay. So now let's summarize what we found after this calculation. We found the following. We found that 6a2 plus a0 is 0. And then 4 plus 1 is 5. And that's 18. So I have 18a3 plus 5a1 equals to 0. These are the first two equations that you get out of the first two terms. And then this one is huge. Yes?
The recurrence equation is just the last summation
It's
set
this
equal
one
to 0.
solved, set equal to 0, and solved for an plus 2
Okay.
for the higher index. So
Thank
we
you.
have to solve this for higher index. So let's write that down. 3 n plus 2 n plus 1 an plus 2. And then I need to add this one and that one and that one, because they all have an's in there, right? So in order to put them together, I should multiply this out. So that's n squared minus n an plus 4n an plus an. That has to equal to 0. So these three equations are what we obtained out of plugging in everything. And when is this equation valid from? N beginning from where? 2n afterwards, right? N is 2n afterwards. So this is only valid for n2 or greater. That should always be attached to your recurrence relation, okay? So this is almost a recurrence relation. We just have to solve for an plus 2. But you also have to write down when it starts getting valid. This is the time when all the factories start producing terms. So you have to write that down. Without it, you don't know when to use it, so it's not good. All right, so let's continue. Let's continue. So we have 3n plus 2, n plus 1, an plus 2, plus 4n plus n is 3n, right? So we have n squared plus 3n, and then an, that's just 1, an equals to 0. So now in order to solve for this, you should move this to the other side and divide. So you have an plus 2 equals to negative of n squared plus 3n plus 1 divided by this thing here, 3 times n plus 2, n plus 1, an. Okay. And n2 or greater, and this is called a recurrence relation. If on the exam, if you're asked, find the recurrence relation for this equation, this is where you stop. You don't have to do any of that, okay? Now, if it says find the first, say, 4 non-zero terms or 5 non-zero terms, actually, if you do 4 non-zero terms you already have something here. Then if it's asking for first 5 or whatever non-zero terms, you actually have to solve this for the higher index, and you get the answer. Okay, so let's see how that works. This one, these two, what do they say? This one says A2 is negative 1/6 of A0. Okay, and then A3 is negative 5 over 18 A1. Right? And then let's just do one more. This is valid from 2 and above. So if I plug in 2, what do I get? A4 is minus 4 plus 6 plus 1, that's 11. And then 4 times 3 times 3. What's that? 9 times 4, 36. Okay. A of 2. But what is A of 2? A of 2 is negative 1/6 of A0, right? So it's negative 11 over 36 of negative 1/6 of A0. So that's 11 over 216 A0. Okay, and if you wanted to do A5, you would plug in 3. But let's just stop here and see what we get so far. Okay, so with these solutions, what are we getting? See, A0 and A1 are the two parameters that can be specified when I give you the initial conditions. So that in terms of our previous case where we had the constant coefficient linear differential equation, we had the C1 and C2 for second order, right? That role is taken over by A0 and A1. So it's okay to have A0 and A1 in your solution, but you can't have any more because it's a second order. You can't have any more than 2. Okay? You can't have any more than 2 parameters. So let's see. What are we doing? At some point, you forget what you're trying to do, right? What were we trying to do? we're trying to solve this in the form of y equals to a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth plus a5x to the fifth, and so on and so on, right? That's how we're imagining the solution is. We're trying to see the power series solution of this equation. And because, because A0 and A1 are okay, it's okay not to know them. These are the free parameters. But because I have A2 as negative 1/6 of A0, I can replace this by 1/6 A0 x squared. Okay? And then this one, A3 is, where's A3? This is minus 5 over 18 A1 x to the third. And then A4 is this one. It's plus 11 over 216 A0 x to the fourth plus da da da. Okay? And if we had more time, we can calculate more terms.
Bless you.
And we could just stop here and say, oh, these are the 5 non-zero terms, right? It's 5 non-zero terms of the solution. You could also sort this out in terms of A0 and A1 and write like A0, this is A0 times 1. This is, if I take the A0 out, that's negative 1/6 of x squared. And there's another one here, plus 11 over 216 x to the fourth, and then who knows what. Then there's another one with A1s in there. A1 times x, A1 times 5 over 18 x cubed, and there should be something here that also has A1, but we don't know. So we get this, and this gives us a better idea of what the general solution of this differential equation is. Okay? See, in the constant coefficient case, we always had solutions like C1 times some function plus C2 times another function, right? And this has the exact same structure as that one, right? You have A0, this is like a C1 times one function plus C2 times another function. What is this function really? We don't know. I mean, it's probably some strange function requiring Airy function, Bessel function. There are some special functions that cannot be expressed by basic sine, cosine, exponential functions or anything. So some exotic functions here, which if you plug it into some computer program, it's going to tell you what it is exactly. But I mean, this is how you get the solution. Okay? It's A0 times some function, A1 times some function. If you want to know more about this function, you can graph it, because if you plug in values to this, you can find the graph of it. I mean, what else can you try to ask? I mean, if you wanted to find the values at x equals to 1, 2, or 3, you can just plug it in here and get the values. So even though it's quite unsatisfactory compared to what we were able to do for the constant coefficient case, this is the best we can do. Okay? And it's not that bad, because we can still evaluate and get the values for it. Okay? So that's where we stop.